Of course, the big deal is, how close do you put the child wells? And we've talked about that. And I think the simulation work that I presented that had been done by Vic Sen and his colleagues at Anadarko is extremely helpful when combined with other information, because it's the simulation of production that's giving you the best, and using multiple sources of data that go into the simulators, that's giving you the best view of what well spacing should be. Now I want to talk about infill drilling and poroelastic stress changes, because it's an issue that's been around for a while. And I'll return to this model that I presented before, when we were just talking about visualizing depletion. But in this case, I'm going to focus both on the pore pressure change and the stress changes that accompany it. This is a very difficult problem to solve because the pore pressure changes are so heterogeneous. The parameters that we put into this model is we used 1,000 Darcys for the hydraulic fractures. That would be corresponding to an aperture of about 1 millimeter. Natural fractures would be 100 Darcys. We're arguing they have an effective aperture of about 0.3 of a millimeter, and the matrix is about 100 nanodarcys. Okay, we have a matrix porosity of 15%, and you can read the other parameters, none of which are unusual, but of course these are models and assumed values. And so these three cases we considered not only help us visualize depletion, but also help us calculate the associated poroelastic stress changes, and what would it mean if there's another well over here with hydraulic fractures propagating, toward the depleted zone of the well that's shown. Now, the starting position for these models are moderate overpressure. We're at a depth of about 7,000 feet, so hydrostatic pressure would be roughly 3,000 psi. So 4,000 is about a pore pressure gradient of about 0.57. A higher overpressure, pore pressure gradient of about 0.71, and a significant overpressure, a pore pressure divided by the vertical stress of about 0.85. The reason for doing this is twofold. One is the larger the initial pore pressure, the more depletion that can occur. So obviously, when we put these wells into production for a couple of years with 1,000 psi bottom hole flowing pressure, we're getting very significant depletion. In the case of the severely overpressured case, we're getting more depletion here, and we're getting less depletion here. The other reason for talking about this is that the higher the pore pressure, the lower the horizontal stress anisotropy. We talked about that early in the course. So we're talking about a more isotropic stress state when it's severely overpressured than we are when the pore pressure is modest. Okay? Then let's put the pieces together. The initial stress anisotropy for this case is, for this, strike slip, normal faulting stress state at 7,000 feet is about 2,000 psi. That's we can derive that a variety of ways. It's quite reasonable. About 1,350 in this case, and about 700 in this case. So much less horizontal stress anisotropy. But of course, in the first case, we have significant stress anisotropy, but modest depletion, because the pore pressure starts at 4,000 psi and it's only 1,000 psi in the well, in the bottom hole flowing pressure. In this case, the stress anisotropy is lower, but there's more depletion. And in the final case, the stress anisotropy is very low, but the depletion is very high. So if we think about this in terms of poroelasticity, right, we have a small delta P, relatively small delta P. So we have a relatively small delta S, and that's superimposed on a relatively large stress anisotropy. Here, we have a larger delta P, and we have, therefore, a larger delta S, and it's superimposed on a smaller stress anisotropy. And here, we have a very large delta P, a very large delta S, and we have a very small stress anisotropy. So if you had to guess, you'd have to guess that as we go down in this direction, the effect of depletion is going to be more and more significant. All right, small depletion, large stress anisotropy, high depletion, low stress anisotropy, a low poroelastic stress change, a high poroelastic stress change, and so on. In this fully coupled model, which is described in detail in this 2017 paper, the mathematics of how to do this in this very heterogeneous material is fairly complex. But there's an interesting way to think about it, and that is that the change in stress resulting from the change in pore pressure is proportional basically to the pore pressure gradient, okay? The gradient in pressure associated with flow, of course, the gradient in pressure is basically creating a body force, and that body force is, in fact, then the stress that gets superimposed on the initial stress state to cause a stress perturbation, okay? So what's really important are the pressure gradients. The pressure gradients then multiplied by permeability and divided by viscosity gives the flow velocity. But the pressure gradients create these body forces, and when the gradient is high and the initial stress state is low, the gradients can create large perturbations. When the gradient is small and the initial body forces are high, then it's going to cause a small perturbation. So let's consider that now with respect to some things that appeared in the literature, which I thought when I first saw them were a little hard to understand, might be the generous way of putting it, and a little crazy might be a little bit less generous. So on the left, what you're seeing are changes in the horizontal stress and changes in stress trajectory. And what you can see is that the stress field kind of goes crazy in the vicinity of a depleting well. You see uniform stress orientations in the far field, but in the near field, it's really, really complicated. It turns out that the reason for this is that the initial assumed stress anisotropy out here is near zero. So SH max is equal to SH min. So the reason such huge perturbations occur is because the assumption is that we're starting with an almost isotropic state. Nonetheless, the resultant stress state is extraordinarily complicated. Now, and this would argue in a way that any time a fracture gets close to a depleted well, I guess all hell breaks loose. So this is what caused Lei and I, this kind of problem to develop this model. And here what we're showing is the change in the stress orientation. We're showing it two different ways. We're showing it in the color, so the angular change is shown by the color. And of course, the angular, the tick marks are indicating the orientation of the stress, and the initial stress was left to right in this model. And so in the case of modest overpressure, predictable horizontal stress anisotropy, and modest depletion, not much happens. If we have another well over here and the hydraulic fractures are propagating away from that well, The hydraulic fractures, might be pulled in this direction by the depletion, but the orientation of the hydraulic fractures as it begins to interact with this first well is not very different from it was originally. In the second case, we see some larger rotations out here, and we see some pretty significant rotations in close to the hydraulic fractures where a lot of depletion had occurred. In case 3, where there's very little horizontal stress anisotropy and significant depletion, we actually see a 90-degree change in the orientation of the stress out here, because suddenly the change in the least horizontal stress is larger than the change in the maximum horizontal stress. What that means is because SH min goes down more than SH max, what actually happens is SH min and SH max change. The change in SH max is more than the change in SH min, so what had been SH max becomes SH min. And that is, in fact, causing a flip, because the old SH max direction is now the SH min direction. The hydraulic fractures change 90 degrees. Now, this is very dependent on how we set this model up, and the assumed initial stress state and assumed properties where we put the fractures, how we do all this. But nonetheless, very significant changes can occur when you start with a condition of very little horizontal stress anisotropy, and we superimpose on that very significant depletion-induced poroelastic stress changes. So if we come back here and look at this case, what we saw in this case was, the fractures were sucked in to the depleted zone around H1 due to this large change in the least principal stress, but the orientation of the stresses wasn't affected at all. The orientation of the stress is exactly consistent with the regional picture. And, if we put this into a normal faulting strike slip stress environment and we look at reasonable values for the initial pressures, it actually turns out that this modeling as scaled for the Bakken, it's probably something between these cases, 1 and 2. So again, as you approach the depleted zone, say, in the vicinity of well H1 with either H2 or H4, the hydraulic fractures are propagating with the direction that one would have expected from the regional stress field. But actually, in the vicinity of H1, if the fractures actually got that far, they would be propagating with some new orientations. In that case, one could envision how the production from H1 might have actually been improved by the stimulation associated with H2 and H4. Now, I still think, and I don't know this, H2 and H4 probably were significantly affected by their hydraulic fractures being sucked into the region around the H1 well, and were probably not very good wells. But it would be interesting to know whether or not the H1 well production actually went up after the stimulation or not. An interesting speculation. And so, this change in SH min that we see out here, would result, a 1 to 4,000 psi change in pressure due to depletion would change the least principal stress, on the order of a few hundred psi when more than 1,000 feet of the well. This is more than enough to affect hydraulic fracture propagation and has important implications for infill drilling. The interesting speculation, at this point is to think about severely overpressured and low anisotropy and high depletion cases and how hydraulic fracture orientation might have been severely affected. That opens up all sorts of possibilities in sort of a brainstorming mode about whether in these areas, new hydraulic fractures would propagate in totally new directions. That's complete speculation, but maybe something worth thinking about.